Okay, so just to recap, so we were looking at the in the branching Brownian motion with absorption, we're looking at the probability that nobody's hit the origin, nobody's been absorbed up to time t. So that's the same as asking that the minimum over the whole time between S and T of the leftmost in a normal BBM, the leftmost particle position over the entire period, 0t, nobody there has got down to the origin, but I'm putting this shift on. I'm going to start at x plus sigma t, right? So I take that sigma t over the other side and put it there. So it's the same as the minimum being greater than minus sigma t. So what I'm looking for is this solution that's, that's converging with time, and it's drifting off. It's drifting off with some speed, right? So there's some speed that it's drifting off with, and I'm hoping that the solution ends up looking like a static shape. It turns to a traveling wave of shape theta x, and that the speed it's traveling with is sigma t. And as I said, I'm guessing that this speed sigma t should be something similar to Bramson. Why isn't it exactly Bramson? Well, Bramson was not about the minimum of the leftmost particle, it was about the leftmost particle at time t. So there's a difference here that we're looking at the all-time minimum. Bramson was looking at the minimum at that time, fixed time t. So for sure our minimum over all time is less than or equal to the kind of corresponding Bramson. We know that that converges to theta x, this critical traveling wave, as long as we take sigma equal to minus mu t minus Bramson's funny mt. So we know what happens over here, but there is an inequality here. But we would guess that the minimum over 0t and the minimum at time t, LT, are pretty similar, and indeed they are, right? So this inequality doesn't make a big difference, and so the theorem is, so it does need some proof. So the theorem is, if we define sigma to be the root 2 beta minus mu t, that's the dominant linear term, we have to have the log correction. Then if we recenter, if we move at speed sigma t, which corresponds to starting at a higher position, then we will converge uniformly to theta of x, to this critical traveling wave shape. So this same shape is just moving across basically at speed sigma t. So it's a very nice result, and that's true for all mu strictly less than root 2 beta. So that's using PDEs, and the idea is to use some comparison and apply Bramson's result. Okay, so that's what happens now for the absorption, nobody being absorbed when we've got this drift, which isn't too big. Okay, so now what happens in the case where mu is greater than or equal to root 2 beta? Okay, so now we want to look at, so let's just go back maybe. Was that the case mu? If the drift is very large, so this is where the triangle is above, even the lower bit of the triangle is above, so we're tending off to the whole process is, BBM is tending off to plus infinity, and we expect there to be, there's only going to be a finite number that get absorbed, and that probability that nobody's ever absorbed is exactly corresponding to the all-time minimum. So now we're going to focus for the rest of the talk on this special case, this case. So we want to investigate initially the function w of x, which is the probability started at x, that no particles are ever absorbed. So again, it's quite easy to see that that's going to have to satisfy a certain KPP equation. So this is from the Brownian motion with drift component, and then if we split, if we branch, then neither of the offspring can ever be absorbed. And they evolve independently, so the rate of change of that is omega squared minus omega. If you split into 3, it would be omega cubed minus omega. Or more generally, you would put the PGF applied to omega, to W there rather. And we've got the boundary conditions that start at the origin, the probability is 0. And if we start at infinity, well, no chance of anyone getting back. So the boundary condition at infinity should be 1. So you might think now that once we've got this FKPP equation with these boundary conditions at 0 and infinity, you might think, oh, well, does that characterize our solution? Is that enough to characterize our solution that W of X, which nobody ever gets absorbed? Well, initially it was a bit surprising to us. Actually, this is not the case. It doesn't, many times this would be enough this kind of information would be enough to give the solution, but in this case it doesn't. Why? Because actually there's infinitely many solutions to this FKPP with these boundary conditions. And so there's a picture here. So basically it depends upon the derivative. You need to specify the derivative at 0. And until you specify the derivative at 0, because each derivative can give a different solution. So here's a particular example of a whole bunch of solutions here that you get if you've got different starting solutions. So there's different derivatives that end up still going to 0. So that's a low derivative, a high derivative here. It might actually overshoot 1, get bigger than 1, and then come back down to 1 from above. So there's infinitely many solutions that we can get according to the derivative at the origin of W. So this corresponds to the fact that the attracting point at 1 at time at X equals infinity, it's a stable or attracting point. So it sucks in many solutions. Many solutions end up tending towards 1, as you can see from here's the level 1, as you can see from that simulation. So the question is, how do you characterize it? What is the what's the derivative that we would have to specify at the origin that would uniquely define this, or is there another way? In fact, there is another way, and the solution that we're after, which is this red one, there's one that really is our W of X. That is the unique solution that approaches 1 the fastest. So there's exactly one solution that approaches 1 quicker than all of the others. So there's basically, when you do a linearization of this about the target point 1, there's 2 possible routes to the 2 exponential decay rates, and one of them's slower than the other. So that one always dominates unless the coefficient in front of that is 0, and then you're left with a unique faster decaying solution. So all of the other solutions have got non-zero coefficient in front of the slower decaying term. When you set that to 0, the constant on the other is specified already by the other boundary condition, so you get left with a unique solution. So it's quite different from other situations that we see in the KPP. So the result that we got from that, that comes out of that, is that W is, well, another way of putting it is W is the maximal solution of 6 on R plus, such that it's always in 0, 1 for all X. So of course these blue solutions overshoot, so they don't stay in 0, 1. And if we want the fastest converging one, actually fastest converging one amongst the red and the greens is the red. Right, the maximal one is the red. The fastest convergence is the maximal one. So it's another way of saying it's the maximal one that stays in 0, 1. Any of the others, if you over push the derivative, you overshoot. And furthermore, there exists some constant such that for large x, we get this exponential decay, getting close to 1 exponentially quickly. And I think the other route is a minus here, and that's the slower approaching one. But we've got a plus here, and that's the fast decaying one. So that characterizes now the solution Wx. So that's kind of a PDE way of characterizing our probability. So just to sort of do a comparison there, if instead we looked at the extinction probability, so if we looked at the probability of extinction when mu was greater than root 2 beta, then we'd find that that we got a very similar PDE for the differential equation for the extinction probability. Again, we've got the drifting Brownian motion generator applied to it. And then if we branch, well, if we want to become extinct and we branch, then both individuals again have got to be extinct. So again, we replace the single particle by the two branching at rate beta to get this extinction. But the change is that the boundary conditions now flip over. If we look at the probability of extinction, if we start at the origin, we'll become extinct straight away. And if we go to infinity, we'll survive, so we'll never become extinct. So where we looked at the probability no particles are overabsorbed, we got a 0 and a 1. So we've just flipped those round. All we've done is flip those round, and now we're looking at the extinction probability. But the extinction probability is characterized by this equation. So there is already a unique solution to this equation when we flip these boundary conditions around. In this case, with these boundary conditions, there was no unique solution. We flip them around, suddenly we get a unique solution. And in that case, that's because 0 as a target. If I'm trying to move towards 0, that's an unstable point, and there's only, if we shoot in exactly the right direction with the right derivative of the origin, only one value of the derivative will lead to the solution ending up at 1. All the other ones will miss, they won't even get to the target. So it's a nice way of seeing how you get unstable versus stable equilibria in nonlinear equations. Okay, so that was a result by John Harris, myself, and Andreas back in 2005. Again, we got a unique solution, and there was similar decay, but it's tending to 0, so you don't need the 1 minus. So that's just as a little nice comparison, So it was one of the surprising complications. When we first looked at this, we thought it'd be quite easy, but that was one of the surprising complications, that we had to deal with all of these other solutions, and it made things like a lot more involved. Okay, so how much have I got left to do? Good question. Ooh, loads. So what next to look at? So that was a lot of PDE stuff. So maybe I could just talk a little bit about where the probability can say some stuff about our probability of nobody being absorbed. So for branching Brownian motion with the drift mu, so a standard branching Brownian motion where there's no killing, no absorption, then it turns out there's a load of martingales, which we call additive martingales because they're sums. There's a load of martingales that basically you sum over all the particles alive, you discount by the branching rate because the expected number of particles alive at time t is e to the beta t. So this is like dividing by the average number of particles. And then each individual particle is moving as a Brownian motion. So this is a bit like a classical Brownian motion. So if I've got a drift mu, I'm just taking off the drift there, so it becomes a Brownian motion. So this is just your standard exponential martingale for a Brownian motion, e to the lambda bt minus a half lambda squared t. well, except I put a negative lambda on it. So, oops. So, where was I?
Maybe page 13. Yeah.
Found it. So, so this is so this gives a nice, you know, it's believable that this is a martingale. If you take the expectation, then it's the sum. Basically, all the particles are behaving the same, so that averages out to be an e to the beta t, cancels off that, and then you just end up like taking an expectation of a standard Brownian motion with the drift. So in our case, if we sum over all the particles, then we have this family of martingales, additive martingales, indexed by minus lambda. So if we take the specific choice of lambda to be r, so this is an important quality, which was the rate of decay that we saw earlier, this mu plus the square root of mu squared minus root 2 beta. So if we choose that specifically, so that's one of the roots of here, that gets rid of this term completely, then we've got a much simpler martingale, which is just the sum of e to the minus r x u of t. So there's no time that we need. We've chosen the r to make that vanish, basically. So that gives us a positive martingale when we sum over all the particles. All the particles in the BBM, no killing. But we're interested in the BBM with absorption or killing at the origin. So how can we relate this martingale for a standard BBM? How can we relate this to the absorbed one? Well, so the idea is that we can actually, because this is a sum over particles, we can kind of stop individual bits of the martingale, individual bits of the martingale in the sum. We can freeze at different times. So we can kind of use these things called stopping lines and freeze individual particles whenever they hit. So if a particle hits the origin, I stop evolving the martingale down that subtree. The ones that stay away from the origin, we keep evolving as this normal martingale. So you do this stopping of particles whenever they hit the origin, and you can convince yourself that should preserve the martingale property. As each individual particle is kind of carrying its own martingale with it. So you can stop individual particles without mucking up the martingale property of the Z. So what that tells us is that we can actually define a martingale for the absorb process, where instead we sum over all the particles that are still alive, that have avoided being killed, or that have been frozen at the origin. So this is the sum over all the particles in the absorbed BBM, where we freeze those particles that touch the origin. Of course, when I freeze them at the origin, then that position is 0, and that just counts the total number at the origin. So this martingale now becomes the total number absorbed at the origin by time t, plus the ones that have avoided being killed, the ones that have never touched the origin, evaluated at their current position. So this is like a stopped version of this standard BBM martingale. So it turns out that this martingale actually, it converges almost surely in an L1, and its limit, in fact, all of this stuff tends to 0, and the limit is the limit of the KT. So it actually converges to the total number of particles absorbed at the origin, almost surely, and in L1. So of course, because it converges in L1, it's a really lovely martingale. It means it's uniformly integrable. It means we can recover the whole martingale by back projecting from its limit. So the value of the martingale at time t is almost surely given by the expectation of the limit, conditional upon knowing what's happened up to time t. So this is our UI martingale, because we've got this nice L1 limit, and in particular, the expected number of particles that ever hit the origin, ever get absorbed, is e to the minus rx, which is quite a nice result. So the higher up we start, obviously the less on average that we expect to get back to the origin. Okay, so so what can we do with this martingale? Why is it so useful? Why is it related to stuff? Well, it's a UI martingale, so I can define a change of measure on f infinity by k infinity over its expectation. So this gives me a new probability measure q. And because it was a UI martingale, if I collapse back to ft, I just get the martingale at time t instead of its limit divided by the value at 0, which was this. So there's a change of measure that I can do with that additive positive martingale. How do I understand this new measure, or the process under this new measure? Well, it turns out there's a very nice description under Q. So under Q, this is like a modified BBM with a distinguished special spine. So you start one particle at X, you evolve it with a modified drift. So it has a modified drift of minus mu square root of mu squared minus root 2 beta. So you run that special particle until it hits the origin. Obviously, it is going to hit the origin. And you speed up births along that particle to rate 2 beta. If you had a general offspring distribution, that would be m beta. But here we've got binary, so it's 2 beta. So you have births along that green path at accelerated rate. And then anyone that comes off those births, they evolve as standard branching Brownian motions with drift mu absorbed at the origin. So these purple subtrees that come off the accelerated births along this special green spine, they just behave as normal. If on the event, so of course, this could be under P, this could be 0. There may be there may be nobody, and the original measure, remember, the drift is going up, so it could be that nobody ever gets to the origin. So K could be 0, in which case Q doesn't see those paths. So the Q measure, when K is 0, doesn't see those paths that P had. But on the event that K is greater than or equal to 1, on the other hand, P and Q are equivalent because this is strictly positive, and you see all of those paths. So this kind of spine construction, first appeared for BBM in Chauvin-Roual, 1988, slightly modified, not for absorb, but there's something slightly similar. So it's a very nice and powerful technique using spines. So, so what can we do with it in particular? Well, we can use this now to give an explicit probabilistic representation of the function Wx, of the probability Wx. So 1 minus Wx, remember, it's just the probability, well, Wx is the probability nobody ever gets absorbed. So 1 minus Wx is the probability that at least one person gets absorbed over the whole time. So there's at least somebody that gets to the origin. So that's the same as the probability that limiting martingale, remember the limiting martingale is just k infinity. So that's the same as the value of the limiting martingale being strictly positive. But now, because the limit of the martingale is strictly positive, P and Q are going to be equivalent. That is the limit of the additive martingale. So P and Q are equivalent on this, so I can write that as the Q probability of 1 over, so dq by dp is that, which is, okay, it's the same as putting in infinity there. So I can, if dq by dp is the ratio of the z's, I can just do it the other way up. And that's fine because I just need to be careful that I don't divide by 0 here, but that's fine because I'm restricted to the event that that's strictly positive. So put another way, this is an f infinity event, so if I want to change the q back to the p, I just have to multiply by the dq by dp, which is 1 over that, which cancels it out and gives you back that. Okay, it's a very simple, neat trick. But now this is Z infinity is K infinity. This one, so this ratio just gives you 1 over K infinity, and then 1 over K infinity times the e to the minus Rx from there. So this now has given us an explicit representation under Q for 1 minus Wx. It's the Q probability of 1 over the K infinity e to the minus Rx. Why is that useful? Well, one of the things that makes that useful is because we've got a nice spine decomposition, as I said before. So the total number hitting the origin is, well, under Q is the spine. Definitely the green one hits the origin. And then it's also, if I sum along the births off the spine, right, then if none of those and the first one ever hit the origin, that'll be a 0. But if in this subpopulation there was 2 that hit the origin, then that would add up 2 for that. So off every birth along the spine, I look to how many individuals managed to hit. So the total number to hit will be the 1 from the spine plus the number that hit off all the subpopulations that are born off the spine. And it's quite easy to see that obviously this is less than 1, it's decreasing, and further, if we let x go to infinity, then it converges to a positive finite limit. So if I started, you can see how you can do this backwards in time now. I can just start from a higher and higher x, and I'm just adding on stuff in the past. So you can do it in a nested way and essentially let x tend to infinity. So you can do it via, there's a very nice way of doing it with this reverse process. There's a nice description of this reverse spine, and then you do the births off it, and it's a nice little probabilistic argument that shows this is going to be finite. So what we get out of that is that we've got this probabilistic representation using this spine change of measure, and we can show that this right-hand side, we know that x behavior, and we know that this, as x get large, converges to a limit, which is in 0, 1, strictly in 0, 1, and therefore we also, that tells us that the asymptotic, the 1 minus Wx approaches 1 exponentially fast, and this is the constant. This is the probabilistic representation for the constant. So that's a nice probabilistic interpretation. So we had a PDE solution for W. Now we've got a nice martingale representation and asymptotic out of it. So might just actually finish. I've got 5 or 10 more minutes is okay, is it? Or am I pushing it?
Yes, it is perfect because the meeting will stop in 10 more minutes.
Okay, great. So the next thing I want to say is look at is actually there's a series expansion that we can get for this probability that nobody gets absorbed at the origin. So we can understand that in terms of a series expansion. So the series expansion is defined. It is explicit. Well, it's implicitly defined by recurrence equations. So we start off with A1 equals 1, and then we get the subsequent ANs. If you look at this formula, we have to do it inductively. The AN on the left, we only need to know about, this is a sum from 1 to n minus 1. So we only need to know about the earlier A's to get the AN. So to get AN, we only need to know about A1 up to AN minus 1. So we can get these inductively. I can get A1, then I get A2, then I can get A3. So this gives me a sequence, a well-defined sequence of A's. And so you'll see why that appears in a minute. And our series solution result says that there exists some B in 0, 1, such that the sum of B to the NAN is 1. And this series converges absolutely. And then we can write 1 minus wx explicitly, and this was a surprise to me because I'm used to the standard FKPP where no chance of anything explicit. You can get representations, but you can't give explicit solutions. But actually, in this case, we can give an explicit solution because of the boundary conditions. They help you out, and it's given in terms of this function phi, which is defined, which is the power series with coefficients defined by these a's above, but evaluated at this special constant b times e to the minus rx. So it's 1 minus wx. It's a power series expansion in terms of e to the minus rx. So on this exponential scale, it's a nice power series. And in particular, that gives us the asymptotic that 1 minus wx must be b e to the minus rx. So looking back to what we had here, this must actually be the b. So actually the b is not a mystery value. It's exactly that q of 1 infinity of 1 over k infinity. So this is again, I found this very nice. So the secret is in knowing that it exists and knowing what to look for. Once you actually guess, once you understand or believe that you might have a power series expansion, as soon as you write wx as 1 minus this sum an and these increasing powers of some constant e to the minus rx to the n, as soon as you plug those in the KPP equation, right, then you can see when I differentiate, right, and I look at this one. So when I apply that to these terms, that'll be nice. That'll just pull down. But we have nice properties of the ANs. And when I do the square, when I multiply two power series together, I'm going to get something that gives me this. So the nonlinear term is going to give me that relation that's going to tell me how these A's are going to be related. So basically, you just look for a solution of that form, plug it into there, and it automatically tells you what these A's should be. At least heuristically. And of course, once you put in the boundary conditions, that gives you this, and it gives you these two things are your boundary conditions from here. So it's believable, even though it's a bit of a work to prove it. Just noting a couple of things, changing the b in the expansion, these should be b's. Changing the b in the expansion just shifts the function. If b equals 0, it gives a constant function. That's the boring solution. If b is negative, so you might ask, well, what happens if b is negative? Because all these a's are positive. What happens if this b is negative? Well, actually, then you get a fluctuating series. You get an alternating series. And then we believe that this series still works, but it corresponds to, instead of the solutions that approach from below, when b is negative, it corresponds to the solutions that go above 1. Very nice. It's a very nice interpretation. So the only issue was we couldn't show exactly what the radius of convergence of this function phi was. So although we could guarantee this for wx, we couldn't guarantee it for all the solutions that went above, because we didn't know how big the radius of convergence was. So there was basically a hole. There was still a conjecture left in our paper that said that this series expansion actually works and gives rise to all the other solutions. Still something to do. If you solve that as an exercise, I'd be very happy. Okay, so I better be quick now. So actually, what we also might like to do, I've just looked at the probability that, that k infinity is 0, but we might actually want to say something about the distribution for the numbers. So what I'd like to look at is the PGF of k infinity, right? So when, whoops, oh dear.